Okay, so today we're going to pull back the curtain on a piece of engineering that is so fundamental to our modern lives, but it's completely invisible. It's the secret sauce inside 5G, and it's the reason your phone works so incredibly well, even in the most insanely crowded places.
Think about it. You've been there, right? A packed stadium, a busy concert, a crowded city street, and you pull out your phone and it just works. You get blazing fast data. But how? How can one single tower serve thousands and thousands of people, all streaming and posting and browsing at the exact same time, without the whole network just grinding to a halt? It seems impossible, almost like magic. Well, it's not magic. It's just brilliant engineering. Let's dive in.
All right, so to really get our heads around the solution, we first have to appreciate the scale of the problem. And that problem is what we're calling the 5G speed paradox. At the heart of all wireless communication, there's a really simple rule. If you want more speed, you need more space. You need a wider bandwidth. It's kind of like a highway, right? If you want more cars to go fast, you can't just have one lane. You need to add more lanes. It's the exact same idea for data. And just look at the jump we've made over the years. With 3G, we were working with a tiny 5 megahertz channel. Then 4G came along and quadrupled that to 20 megahertz, which felt like a big deal. But 5G? Whoa, it blew the doors wide open with a massive 100 megahertz channel. Now that huge highway is what allows for those incredible speeds. But, and this is a big but, it also creates a brand new giant of a problem. Yeah, see, with all that extra bandwidth, we accidentally woke up a monster. A monster that's always been lurking in the airwaves, just waiting for its chance. And its name is multipath. You see, in a perfect world, a wireless signal would just zip in a nice, clean, straight line from the cell tower right to your phone. But our world is anything but perfect. That signal bounces off of everything. Buildings, cars, walls, even other people. Every single bounce creates a little echo, a slightly delayed copy of the original signal. So what your phone actually gets is a whole flood of these jumbled echoes arriving at different times. That mess is what engineers call a multipath channel. Now, when you're using a super wide bandwidth, like 5G's 100 megahertz, that multipath effect goes into absolute overdrive. It's not just a few echoes anymore, it's a signal storm. All those echoes just crash into each other and completely scramble the data. Imagine trying to have a conversation in a huge cavern where 100 echoes of your own voice are all coming back at you at once. It's just chaos. So for an engineer, that big, beautiful 100 megahertz channel suddenly looks like this, a jagged, unpredictable, unmanageable mess. Trying to send one coherent stream of data through that is practically impossible. This was a massive roadblock. So how on earth did they fix it?
Well, the solution wasn't to fight the chaos head-on. You couldn't just power through it. The solution was much more elegant. It was to outsmart it, using a classic, beautiful engineering strategy: divide and conquer. And this idea right here just nails it. When a problem seems impossibly complex, don't try to solve it all at once. Break it down. Chop it up into tons of tiny, simple problems that you can solve. And that is the core idea behind the technology that makes 5G possible: orthogonal frequency division multiplexing, or thankfully just OFDM for short. So here's how it works, and it's so clever. OFDM takes that one giant, chaotic 100 megahertz channel, and it digitally slices it into thousands, like 3,000 tiny little independent subchannels. Then, instead of trying to blast all your data down one chaotic fire hose, it sends just a tiny, manageable little piece of data on each of those tiny channels, all at the same time. And this is the aha moment. This is the magic trick. By splitting that one big problem into 3,000 small ones, the whole landscape changes. We go from that single, chaotic, jagged mess on the left to thousands of beautiful, simple, flat, and totally manageable lines on the right. Each one of those little subcarriers is now so narrow that the multipath chaos just doesn't affect it. All of a sudden, the channel is predictable. We tamed the monster. But here's the really cool part. This simple act of dividing and conquering doesn't just solve the multipath problem. It unlocks some truly incredible new abilities. Let's call them OFDM's 3 superpowers. Okay, so what are they? Well, first, as we just saw, it tames that wild channel, making it super easy to clean up the signal. Second, it lets the network get incredibly smart about how and where it sends your data. And third, and this is the big one, it's how we can seamlessly serve tons and tons of users at once. You know, our whole stadium problem. So, superpower number one is something engineers call equalization. Sounds fancy, but it's pretty simple. Because each of those little subchannels is now a nice, flat, predictable line, your phone can easily look at it, measure exactly what the channel is doing to it, and then just digitally erase the distortion. It cleans the signal up perfectly, something that was a total nightmare on the old wide channels.
Superpower number two is smart scheduling. This is where the network basically gets a brain. It can now see the quality of all 3,000 of those tiny channels individually, in real time. It knows which ones are strong and clear, and which ones are weak or faded. So what does it do? It's not dumb. It intelligently routes your data only onto the best, strongest, clearest channels available at that exact split second. This maximizes your speed constantly.
And this is it. Superpower number three. This is the one that answers our stadium question. With thousands of these little subcarriers to play with, the network can do something amazing. It can assign a small block of them to you, another block to the person next to you, and another block to someone a few rows back. It carves up that huge 100 megahertz resource and shares it among many users at the exact same time. This is called OFDMA, and it is precisely how one tower can serve an entire stadium full of people without breaking a sweat.
So this all sounds fantastic in theory, right? But how in the world do you actually do it? How do you digitally slice and dice a radio wave in real time? Well, that brings us to the real magic that's happening inside your phone.
You know, the funny thing is, the idea for OFDM has been around for decades, but for the longest time, trying to actually build it required a total nightmare of complex, expensive, room-sized analog circuits. It just wasn't practical. The real game changer, the breakthrough, was when we figured out how to move the entire operation from clunky hardware into the elegant world of software, into digital algorithms. The digital engine driving all of this is a brilliant pair of algorithms that have opposite jobs. Think of them as a team. At the cell tower, an algorithm called the IFFT takes your data and digitally and very efficiently spreads it out across all those thousands of subcarriers. Then, inside your phone, its partner, the FFT, does the exact reverse. It grabs all that data from each tiny subcarrier and reassembles it perfectly. And that right there is the real punchline. The idea of OFDM was brilliant, no doubt, but the actual breakthrough that changed our world was the creation of tiny, powerful computer chips that could run these incredibly complex algorithms in real time, right inside the device in our pocket. That immense processing power is what finally unlocked 4G, and now it's the very foundation of 5G. When you step back, the story of OFDM is just a perfect example of elegant engineering. It's a massive, complex problem that's solved by a simple, almost beautiful idea, and it's all completely invisible to us. It just works. And that kind of makes you wonder, doesn't it? What other hidden marvels of engineering, what other invisible masterpieces are quietly powering the world around you every single day?